Welcome to the second day of the class. Today we will dig a bit more into the antennas. First lecture is about the historical development. Some of you, they all have good background because of the training in the technical university. Some of you don't have any background of electrical engineering, so we will balance in between these two groups. As I said yesterday, my name is Peter Petkov, associate professor in antennas and microwaves. Okay. Let's start with what we have known so far about antennas. If you can identify some of them here in the picture. Have you seen some of this?
Yeah.
Yeah.
Yes.
The first one here is a nerd station antenna. It is intended to communicate with the satellites.
We mostly see in satellite TV.
Yes, the uplink, the signal that is transmitted from Earth to the satellite is transmitted through antennas like that with large aperture. Satellite receives, down converts it, and send it back to Earth. And you can receive it with small antennas. So this is a typical Earth station antenna. The second one,
Yagenten.
yes. Where is this used?
For directional purposes.
And in general practice? What for we do use Yagis in present days? And in the past? Television, reception. Until recently, the television broadcast was on analog modulation and horizontal polarization. So this type of antennas was oriented horizontally and was seen about every roof in the country. Eventually, cable television gained popularity, and people decided to switch to cables because it offers more TV programs. Eventually, the standard for digital broadcast moved from analog to digital, which allows reception with a lot of TV programs with high quality. However, the companies that provide cable television or IPTV already gain strength. So when this transition to digital TV happened, it was artificially limited to very few channels. So they cannot compete with already existing cable TV companies. That's why terrestrial multiplexes doesn't have so many programs, because the law forces them to use only a very small portion of the spectrum. So digital TV, particularly in Bulgaria, is not so popular, not because it's not a good solution, but because of regulation favoring one or another player. But in a lot of countries, digital television is highly popular. It is modern, good solution, and antennas for this TV broadcast is EAG antennas. On the third picture,
arrays of antennas.
there are three types of antennas on the picture. The lowest row is base station antennas. The white boxes are just enclosures, and inside there are an array of dipoles which form non-directive pattern in horizontal plane and directive pattern in vertical plane, and cover 1/3 of the base station cell. On the second row, over there, it's parabolic reflector inside the cover, which provides point-to-point link. So these base stations connect to something else. Maybe the source of the signal, maybe adjacent cell with this parabolic radio relay link, antenna link. And on the top of the tower are antennas for personal communications, like police, emergency, fire department, etc. This is a typical communication tower. Here was one of the wonders of the world, this Arecibo radio telescope, which used to be the poster picture of advances of American radio astronomy for many years. However, due to negligence of the government and serious underfunding that lasted years and years, one of the cables that support the feed structure here, if you see there are 3 cables that support the feed, and by moving the cables around and respectively the feed, here is a radio room where people go in, switch the feeds, switch the horns, move this structure around, you can watch different parts of the sky. And this is very large structure in Puerto Rico. So the folks from the government limit the funding of this structure. The cables were under-maintained, and one of them broke. And all these structures, the three structures fall in the reflector and irreversibly damaged the telescope. This happened 2 years ago. And now the Chinese have the biggest one. So, sad but true. There are rumors that they will find money to repair it, but it's not easy to find persons that know how to calculate so complex structures anymore. It's not like writing Angry Birds game or song. It's a little bit more complicated. This here is the radio station of Vaccarel, nearby Sofia, which was built by the structure itself by American company for a long and medium wave, and constructed by Telefunken in the time of World War II. And Europe, there are only 6 of these antennas. And the whole structure is operated by a single man. So one man can lift the tower and replace the ground insulator if it's necessary. And here is a coax cable running in, and nearby is the transmitter, oscillator, and modulator, matching network, etc. However, 2 years ago, the management of former Bulgarian communication company decided that there is no big use for this structure, and it will be better used if it's demolished and built a village for programmers and IT specialists that will love to live in this so-called Vaccarel Swamp, because there is one. The people that will buy houses, they don't know that. And they collapsed the whole structure, and now they are trying to build houses in the middle of nothing. But because the market is hot for housing, they plan, they think they make a great money. Big business here. If you have seen Borat, perhaps you know the phrase. And the last thing is a typical GPS antenna, which you can find in a lot of devices. And it's built over ceramic high permittivity structure. Okay. And let's see what is the relation between antenna size, frequency, and the wavelength. There are 2 groups that I would like to ask you to identify. What are these 2 groups of antennas?
Directional and non-directional.
Yes, they can be divided in this way.
Maybe low frequency and high frequency.
Yes, this is part of the answer. Please, Mohammed.
Maybe there is the dish one or the parabolic and the logarithmic or this dipole antenna.
Very good answer for astronomer, actually. Earthquake. So, if you can take a closer look, some of the antennas are built of wires. And some of the antennas, they form an opening. In Latin, it's called aperture. Like on camera, aperture priority means constant opening of the iris. Here is the same. And antennas that work with wires are similar in length with the wavelength. And antennas that work with aperture, with opening, are much higher than wavelength. These are two completely different classes and radiation principles, as you will see eventually. So how big is the wavelength here? How long? On 10 gigahertz? Three
Millimeters?
centimeters. Close. 3 centimeters. You can barely see it. Here on 3 gigahertz is 10 centimeters, but compared with 300 meters, the aperture is much larger than the wavelength. Here, 500 megahertz is how much?
Centimeters.
50. 1 gigahertz is 30, so half will be 60, close to what we have say. This is called half wave dipole. So this is half. So this is two distinct classes: aperture antennas and wire antennas. And now let's talk a bit the applications that antenna are employed. First of all, cellular communications. This one here is a weather radar. Under the dome, there is antenna spinning and detects where the tornado is coming from. This one here, you have seen this on airports. This is called airport approach radar. When the plane comes, there are of course a lot of systems that tracking the airplane. It reports its own position also based on GPS readings. They are the most accurate. But in aviation, nobody relies only on one system. And the airport approach radar is one of the most field-proven solutions. So the dispatcher knows where the airplane is, regarding whether the airplane reports its position or not. And also if enemy approaches or somebody with damaged system approaches the airport, he can see it on the screen. And on the top of it is IFF antenna. IFF means identify friend or foe. So they know if the airplane is one of us or the. This one here, it's a satellite with, there are plenty of antennas on satellite. This set of forest communication antennas. Here on the earth deck there are also a lot of antennas for telemetry, tracking and control, emergency communications, something, connection with the ground station. Right. And these are the main communication antennas. So the satellite television comes from some of these things. And this here, what is this thing? Pyramids? No. It's a phased terrain for early ballistic missile detection.
From which country is this?
USA. This aperture here is, every dot is a small feed horn. And then if we combine thousands and thousands of them, they form one aperture. And on this aperture we can very well control the phase and amplitude of the transmission and reception first. And when we control the amplitude, the phase mainly, we can control the direction of the beam. So this array can scan electronically. It's not needed to rotate as the airport approach radar. However, once the antenna starts to scan, the main beam starts to deteriorate. And if the scan angle is large, first the beam is deformed, second it forms additional beams that we don't want. This limits the scan angle. And if the scan angle is limited, then we have to put another in order to cover another sector of the space. Something like that is our future radio telescope. The principle is pretty much the same. Yes?
Yeah, okay. Why some antennas are covered with a dome and some antennas are exposed to the atmosphere?
Those who are sensitive to snowfall and rain are covered with a dome for protection. And those who can work in almost all conditions or are employed in non-critical applications, they can work on, like TV antennas. If something happens with the TV, who cares? Nobody. But if antenna is for radio relay, then a lot of people rely on this antenna. So all measures must be taken in order to provide the constant link. And because radars are expensive and they degrade the performance of the antenna, it's up to engineering decision whether it should be employed or not. Who are these two guys? Henry Hertz, perhaps everybody knows it. What invented Hertz? Everybody has heard the unit Hertz. What is first unit Hertz? What does it mean?
Oscillations per second.
Oscillations per second, or even simpler, repetitions or cycles.
Waves.
Cycles per second. It's not necessary to be an oscillated bit periodic signal. Cycles, and this is the unit for frequency actually. Cycles per second, CPC. This is named after Hertz, but Hertz didn't invent the frequency. He invented the first wireless transmission of signal. He built this device, which is a battery, capacitor with a switch, auto transformer, and sparking gap on one side. And on the other is a loop with two closely located spheres. And when we close the switch or open the switch after the coil is charged, in this circuit oscillations start because it's a resonant circuit. And once the oscillations start, the magnitude of the voltage is amplified through to the transformer coupling. So high current, low voltage in this circuit is transformed to a low current, high voltage oscillations in this circuit. And because the voltage is high, here a spark happens between these two spheres. And in adjacent loop, which is happen to be tuned to this frequency of oscillations here, spark also ignites between these two spheres. And it was like one placed here and the other placed here, and this was the first wireless transmission of signal. How he invented that? I don't know. No, it's simply impossible. Who imagine 200 years ago that you barely know anything about electricity. It takes to be a genius to invent such things. But Hertz did it. And the second folk is James Clerk Maxwell. What does he invent?
He unified electricity and magnetism, I think.
The father of electromagnetism.
Theory, yes. He wrote
Four equations.
the Maxwell equations in order to torture the students of electrical. I'm just kidding. He wrote actually 30 equations, where these four of them are kind of a foundation of the electromagnetics. And also his work is called Treatise of Electromagnetism. It's freely available. If someone has time and brain to read it, I highly encourage that, to see what's within the mind of a genius. And Eventually we will discuss what these equations mean. They look scary, but they make sense after and then dig a bit. So these folks are the founding fathers of electromagnetic theory. Alexander Popov and Guglielmo Marconi, everybody knows them. Who did what? They both are claimed to be inventors of the modern radio. But Marconi kind of has the primacy. He actually was first provided radio communication, and Popov actually was also a very prominent Russian inventor, but the Russian Academy of Science neglected his works. And in a time of disaster of one of the ships in St. Petersburg Bay, he was asked by the mayor of the city to help the evacuation of the crew and the cargo. They told him, oh, you mentioned that you have some device that can provide remote communication. Yes, I did so. So go there and put your radio. They didn't call it radio. Put your device there. And he proved, actually, that his invention works. Before that, it was highly neglected, like, oh, what is this piece of shit? And Marconi provided the first transatlantic communication. Actually. Like, this is Popov's receiver, and this is Marconi transatlantic station. First signals were just clicks, like knock, knock, knock. And the operator has to distinguish them between all the disturbances of the ionosphere, because if you turn on your AM radio, you can hear a lot of noises. This is the normal background of the ionosphere. You hear a lot of things. And the first operator has to distinguish this knock, knock, knock. Would you pardon me for a second? Should this one let these guys here?
Yeah.
Udayak, yes. These are two guys. Uda was a professor in University of Tokyo, and Yagi was his assistant professor. And eventually, Yagi moved to the United States and patented the antenna that actually Uda invented, and became very popular as Yagi antenna because of this kind of a not very fair deed. But the inventor of the antenna is Uda, and invented it in circa 1926. And as we discussed, very popular for terrestrial applications. Terrestrial television, terrestrial radio. Why the elements are oriented horizontally here, and they were oriented vertically here?
Because polarization.
Yes, but what was the reason to choose horizontal over vertical in the past?
Lower
frequencies.
They work on the same frequency, basically.
Ground inflation.
Yesterday, Professor Balafot said about propagation of which waves propagate better, horizontal or vertical polarization? Vertical. But then why the analog television was built on horizontal?
Maybe we are aiming to detect the reflected wave from the ionosphere coming in a higher angle.
The reason is way more
I think we
prosaic.
need to clear the noise from other signals.
Yes, this is the reason. And other signals are usually electrical motors, spark sources, etc. And analog television is very prone to these industrial noises, which are mostly vertical. And if antenna is designed for one polarization, it is not sensitive to another. And by this trick, simply you don't see the noise over your screen if the neighbor is drilling with a hand drill. You know, there is a program that no matter where you move to live, the neighbor with the hand drill will always find you. And to prevent that, people used to work with horizontal polarization, which doesn't propagate that well, but is more immune to noises. And now with the change of the standard for television to DVB-T, DVB-T, digital video broadcast, dash terrestrial, that word, in DVB-T, which is fully digital. It is fully proof against industrial noises. So that's why they switched to vertical, which ways propagates better and farther than horizontal. Yes. And eventually, with these antennas, people start to sell the exploitation of higher frequencies. And with higher frequencies, wire antennas became less and less effective. And it means with one antenna you can extract less and less energy. And people start to sell other types of antennas that can help them to receive stronger signals, to receive more power within a given transmission. And they start to resemble human ears, for instance, and that's how the horn antennas start to develop. By the way, cosmic background was detected with wire antennas, but eventually, very soon, people switched to horn antennas. Initially, horn antennas were built for detection of airplanes by listening to the noise of the engine.
So it's not an electromagnetic antenna, it's a pressure antenna.
Yes. But that's how it originated, with a concrete parabolas, and in the focus was an observer that was meant to hear the coming German bombers over the United Kingdom.
Mm-hmm.
And this worked very well for 2 or 3 years until the bombers improved and their speed rises from, let's say, 100 kilometers per hour to 300. So from the moment of detection to moment of reaction, there was just a couple of seconds, and this proved this type of detection useless Because the moment he hears, the bomber is already there and can drop the bombs. But this gives a clue to engineers. Let's replace the sound radars to something more sophisticated. And that's how the modern radar systems develop. So, parabolic antennas were invented about 1935, and military-driven application. Along with that, guys that was fascinated with Udayagi antennas soon realized they can stack antennas in a larger identical structures. And this was the first step toward so-called antenna arrays. And eventually, a whole branch of this science developed because antenna arrays have unique properties, has its own laws, of course based on the physics and math, but they are very specific, very interesting part of the science, and the modern half of the modern radio astronomy depends on these antennas. The other half is still with parabolic antennas, and the third half is for the classical optics. So this is the three branches. Antenna array start. As you can see, this antenna science is pretty mature compared to other sciences, but it always has something new to present. And this is because of the sole fact that the way that electrical field is generated and propagates is not quite clear. We have great theories, but they are still theories. They are not completely proven facts. I'll dig a bit into that in the next slide. Next section. In 50s, one great American scientist, John Krause, sitting at his home, invented the helix antenna. And what is this antenna used for? Just for about everything that you can imagine. Initially, it was placed on spacecrafts because of one very important reason. It gives almost perfect circular polarization. And if you know, a lot of frequencies, EM signals with most of the signals passing through the ionosphere, they depolarize. What does it mean depolarize? It means if you transmit signal with vertical polarization, it will shift the polarization plane. So your antenna, if it's aligned with the origin at the beginning, eventually during the transmission, will see impairment in the reception. If it's vertical, horizontal, horizontal. If a circularly polarized signal passes through the ionosphere, what will happen?
It will still keep circularly polarized, but
It will rotate a bit, you may see some phase shift, but nothing else than that.
Yeah.
So you will still have a closed reception.
But what exactly does circularly polarized mean?
We'll discuss this. I will tell you in one word. The tip of the E vector makes a circle when he propagates.
So it's like a spiral.
Yes. If you take a look on one single vector that propagates, it forms a spiral in a time, considering the time of the finite velocity. If you look behind the antenna, exactly like this man, this is how the sense of polarization is determined. You stand behind the antenna and watch toward the propagation direction. If it turns clockwise, it's called right hand. If it's turned counterclockwise, it is called left hand circular polarization. And this was a great problem with the first satellite. The American team mistake the sense of polarization, so they couldn't receive the reception from the satellites. Fortunately, the British, they were aware of the fact that if you look toward antenna and behind the antenna, this changes the sense of polarization, so they did it right. It was able to receive the signals from satellite. So you know, if the helix is wounded this way, is one of the type of the polarization, and if you wound it other way around, you switch to the opposing polarization. So, yes.
Is it possible to make two spirals like
Combined.
combined? To
Yes,
same
absolutely.
signal?
Yes. So you can switch, and if you combine it properly, you can make linear polarization by combining two circular. This is also doable. Patch antennas, my beloved ones. They are invented in the 70s when people were starting to look for inexpensive solutions based on planar structures like PCBs. Eventually, they used to be top military secret. Nobody knew how they work. Eventually, theories were built around how does patch antenna work. And now they are the working horse of every modern communication.
Who invented it?
Was an American guy with a French name. Barely. I can check for you. Patch inverted F antennas. The patches were modified structure. Notches are made either to improve the bandwidth or to change the polarization or both. Maybe decrease the size. But this type of antennas are embedded in your cell phones. So all the modern communication rely on that. The fractal antennas, they developed with the fractal geometry and the science behind in the late 90s. And contemporary state of the art. RFID bank card, this is how you wirelessly pay. You have a loop, another loop which communicates, it's coupled with the loop of the chip. That's how you pay the bill in the shop. Typical Wi-Fi module inside your laptop. This cable will go to your... Actually, this is a picture of this one. So here are the patch antennas in the screen. RFID tag. As you can see, the chip is here. It's matched with the antenna. Metamaterials. So these metamaterials help us to reduce the size a lot. And 4 and 5G antenna arrays. Questions? Yes.
Meter material, what does it mean?
That it does mean that this material have either negative permittivity or permeability, or both. All materials in the world has positive electric permittivity and magnetic permeability, unless this human-made artificial materials which have negative permeability or permittivity. But this is happening only in very narrow frequency bands. They are not broadband materials. They work very well in very narrow frequency band.
In the low frequency range or high frequency?
No.
Low frequency.
Low frequency, maybe a couple of kilohertz, maybe megahertz. Metamaterials. That's one of the future things, and I'm very eager to develop something like that because you can make a parabolic reflector with a flat surface. And you can stack it on a satellite and launch. No need to make a large concave structure which is hard to stow and launch. You make it foldable, and once launched, unfolds and works as parabolic reflector. This is very typical application. 10 minutes break, like snack. Continue with other great things. As you can see, highly interesting things around us. They're not simply like